So, as promised, I'm back again. This time with a little animation, which is just as valid as Chris UK's one. In fact, it's more valid because I've actually used it to explain what's going on, rather than uh, coming up with some maths out of shot, finding an answer and saying this is what this says. His animation misses some things. So, first off, I just want to recap what we understand by displacement and velocity, or average velocity in this case, because it's not continuous, so it has to be an average, and average acceleration. So if we've got point A, point B, point C, and we move from point A to point B, this is our displacement, the distance travelled. Then we move from point B to point C, this is the next displacement, the distance travelled. If we want to find the velocity, we can just take the displacement and divide it by time. And if, say, point A was at 0 seconds, point B was at 1 second, point C was at 2 seconds, we'd be doing 1 second time steps, and that means that displacement is just the same, but in meters per second as opposed to just meters. Then, if we want to find the average acceleration, we have to take these two velocity vectors and find the change between them and divide that by the time. So we take the two vectors and we divide by the time. This vector here, this purple one, is the acceleration. No, sorry, it's not the acceleration. It's the change in velocity, which in this case, because our time step is 1 second, it's equal to the acceleration. Okay? So here you go. These blue lines displacement, divide by time, in this case 1 second, to get the velocity. It's the red lines. To find the acceleration, take the difference between the two vectors and divide by the time. The purple line. Right. So this is a representation of a rotating object, either stationary or as viewed when you're on board, say, a train moving with the rotating object. I'm going to play it now. It's got 30 degrees per second of rotation. That's the speed. In PowerPoint, that was just 2 rotations for 24 seconds. This is how I animated it. One thing to know is that you can't have the soft start and the soft end enabled. You have to set that to 0 seconds. Otherwise, you'll have an acceleration accelerating up as it rotates and then slowing down as it slows down. So we're talking about instantaneous velocity. So you can literally put a piece of tracing paper on your screen and go through the steps I've done to determine vectors for the accelerations, and you can see exactly what I'm going to show. But I'm going to run this now. So it just rotates like that. This green cross is the point we're looking at. It's rotating the circle. The whole circle in this case is rotating, and I've superimposed the cross on there, so you can see that it's rotating, because obviously if you have the circle just rotating, you won't see anything. So this is how we can measure it. So if we take a 1 second step forward in time, we get the displacement from one point to another. Okay, we do that all the way around and we get a series of straight lines that approximate a circle. That's hardly surprising, that's exactly what you'd expect. So as the steps are 1 second, these vectors here are actually the correct length for the velocity as well. So we could just change them over to the velocity. Then, if we take the difference between the two vectors, we get these purple arrows, which is the change in velocity divided by 1 second gives us the acceleration. These vectors are the acceleration. Okay? Simple enough. Now, We could do it with numbers, but apparently the real world and math are different things, according to Chris UK. So this aim here is just to visually represent what you would get if you did this experiment in real life as well. Like I said in my previous video, I may break out my Lego train and do it. I'm going to be told I'm wrong, so I probably won't, because, well, it's just a waste of my time, to be honest. So yeah, so these are the accelerations here. Now let's do the same when we add in a linear translation. So here we go. This is what it looks like. This line goes from the center of this circle to here. It's 24 units long. I'm saying 24 units. It's measured in centimeters in PowerPoint, but of course, if I zoom in, it's no longer the same length in centimeters. So I've just used units because you can just use units if the whole thing's scaled correctly. This unit could be meters, centimeters, whatever. We're not actually caring about the actual values. We're just caring that the values that come out will be the same. So let's watch it. Here we go. Doo-ba-doo. Rolling along. It's almost like a wheel on a car, except it's moving slightly faster, I believe. Time it takes to do one rotation. I can't remember. It might be that it's like a car wheel slip. Well, it will be like a car wheel slipping and sliding rather than a car wheel that actually is gripping the road properly. Yeah, so that's that. Again, we take the same method. Here we go, displacement between 2 points, and we go all the way through and you get this nice line. Now, this is what Chris UK is getting confused about. He's saying here the velocity is really high, but here the velocity is really low. And that means that must be a massive acceleration between there and there, right? And because this line is just a little bit shorter than this line, but this line, sure, is much shorter than that line, it's a huge change in acceleration. Now, if you're just viewing a one dimension, the z-axis, along this motion, this line of motion here, then you would see, you know, big speed, little speed, little speed, little speed, little speed, little speed, bigger speed, bigger speed, bigger speed, bigger speed, and that's what you would see. So I guess, say, if you were to view this setup from the side, you would think potentially that it was slowing down and speeding up in this direction, completely neglecting the fact that actually it's getting closer to you and further away from you as well. So I accused him in the comments of one-dimensional thinking. This is why. He is thinking in one dimension. He's flattening this onto a straight line and going, oh, it's speeding up and slowing down, and therefore massive acceleration and changing acceleration. No, that's not what's happening. So we take this displacement and we divide it by 1 to get the velocity.
Mic off. Mic on.
Sorry, that was really bad. Yeah, we take the displacement, we divide it by 1 to get the velocity again. Okay, so the lines don't change in length. Then we do the same. We compare the velocity at one step with the one from the next step, get the difference, and we get this series of vectors. Now, this might blow some people's minds. If you understand what's going on in physics and inside, say, a car wheel, the forces inside a car wheel, this won't blow your mind. Look, they are the same. Now, obviously, I say they're the same. They're not quite the same because I've drawn this with lines, you know, but there's no huge changes. Like, none of these are half the length of another one. It's all within the realms of me trying to get the right length when I'm doing this, lining up one point to another. Okay, so basically this is the maths of why it happens. And so Chris UK has calculated the resultant velocities here by taking the linear velocity and adding the tangential velocity. This was all in vector form. He did good there. Where he failed was he went, right, this is my vector, this is my other vector, and actually instead of vectors, I'm just going to take the magnitude of this one and minus this one from it to get my change in velocity. That's incorrect. If you actually work it through, you go, these vectors are the same, so they cancel out. You're left with the tangential velocity vector at one point and the tangential velocity vector at another point. And those are not magnitudes, those are vectors. That is the important thing. So to recap, this motion and this motion have the same forces acting on them. This one is from an outside observer, this is from someone moving with the object. Or this is when there's no linear velocity. If there's no linear velocity, i.e. there's no relative velocity between you and the object you're looking at, then you are moving with it. You are moving in that reference frame. Okay. This is how a change in reference frame affects things. Okay. The point here does not feel any different. And he was saying about fairground rides. And his claim is, if I'm right, fairground rides don't work. Okay? The reason fairground rides work that are, say, a motion similar to this, I'll explain why similar in a minute, is that they are speeding up and slowing down in this direction as well. You're at 0 here and you're heading that way. You are adding an acceleration. So you might be 0 miles per hour here, then you might be 10 here, and then you're 0 here again. And then you're 10 here, and then you're 0 here again. And so say 0, 5, 10, 5, 0. That is how a fairground ride will work. How do I know this? I'm friends with someone who works and designs fairground rides because I'm an engineer. And funnily enough, engineers tend to hang out together. We do all sorts of different things. Yeah. And then on a waltzer, the reason that, with a, or not, is it a waltzer? Let's go with teacups. On teacups, you've got a rotation on a rotation. And at certain points, all the acceleration is adding together towards the center of the large rotation. At the opposite point on the little rotation, the accelerations are in opposite directions, so they reduce the resultant acceleration. And then at the sides, you add them together and you get a sort of sideways one. That is how those work. And I can do an animation showing that in the physics. I could do it, or you watching this video could do it. Anyone could do it. We could also take real life footage from above a fairground ride, do exactly the same analysis as I have done here, and it will show you why the accelerations change on the fairground ride. You could also do this animation with something in real life. Like I said, I might break out my Lego train and do it at some point. Not sure at this point. Seems like a waste of time because I'm hitting my head against a brick wall because Chris UK doesn't want to understand the physics he's trying to explain. Yeah. So, yeah, thanks for having a look at this. I can give people this PowerPoint if they'd like it. Mess around with things, change some of the values. redo this tracing out, you can do it on this video. Tell you what, I'll just play this animation again, and the other one. So here you go. Here's the rotation from a stationary, from when you're in the same reference frame, or a stationary object relative to you. It's a bit boring to watch, to be honest. Exciting. You could speed this up to like 20 times if you wanted. You could speed up the the linear speed on the other one to 20 times if you wanted. You'd see exactly the same thing. Yep. The only difference would be the size of the acceleration. When something's rotating faster, the acceleration towards the center is larger. If it's traveling faster in a straight line as well as rotating, then there is no difference. Just wait for this one to complete. Right, there you go. And the way I got this to move from one point to another, you'll see that it's an equal shape. I've made it so that it's, when I rotate this, it rotates about the center. And I went to, is it here? No, I have to click it, don't I? Size and position. Here you can do the rotation. You can say set it 60 degrees and then add 1 centimeter in horizontal motion. Sorry, add. There you go. That's the next position. Easy peasy. Okay, cheers.